And thank you all for waiting here to the end of the day for my talk on the shared future of arc and LED UV curing systems. So a few words about us before we get started. GEW is a privately held company which was founded by the Ray family in 1991. We specialize in manufacturing UV curing equipment for a range of both mechanical and digital printing machines, as well as machines which apply both decorative and functional coatings. The transition from curing with mercury arc lamps to UV LEDs is already well underway, and the move is not always fully understood, particularly amongst the end user market, for both technical and financial reasons. And in addition, there's a lot of speculation about when mercury lamps are going to be replaced by UV LEDs. So what I'd like to start by doing is bringing some clarity to the debate by first exploring the differences between arc and LED systems in terms of how they operate and in terms of how they cure the ink. So UV curing. This is an umbrella term, curing performance, which not only looks at physically how well the ink cross-links, but also some of the more subjective properties, such as the quality of the finish, how well it sticks to the material, what the adhesion's like, how well the surface is cured. And that's actually governed by a range of factors which we call the curing equation. And for optimum curing performance, all aspects of the curing equation have to be understood and fully balanced. So let's have a look at that. The curing performance is made up of both the UV dose and the UV intensity of the UV light source, the thermal footprint of that light source, and also chemically and physically, the properties of the ink itself. So dosage and intensity, when thinking about that, a simple analogy to consider is driving in a nail with a hammer. So the dose is a bit like how many times you hit the nail, and the intensity is like the weight of the hammer. So it stands to reason that using a heavier hammer is going to be more effective at getting the job done. And for that reason, intensity is absolutely critical for effective UV curing. Another very important factor is the thermal footprint. So heat is necessary for an effective chemical reaction to take place. If you look at this diagram over here, at low temperature, there's a relatively slow rate of molecular collisions. So when you've got your photoinitiators, which are activated by the action of UV light shining on them, they form radicals, and what you want to happen is for those radicals to then collide with the monomers in the ink and cause the polymer network to be formed. Now at low temperature, that happens at quite a slow rate. At high temperature, the speed at which these molecular collisions occurs takes place at a much higher rate, so your polymer network forms faster and the ink cures faster. So more temperature is generally a good thing as far as the chemical reaction is concerned, and as a general rule of thumb, if you increase the temperature by about 10 degrees Celsius, that will result in a doubling of your chemical reaction. However, there has to be a balance, because if you increase the temperature too much, then potentially you can damage the substrate. And where many heat-sensitive materials, films, etc., are being processed, that too much temperature is obviously going to be undesirable. So there is a balance there. The footprint of the heat output needs to obviously be optimized to the application. The ink properties themselves also have a very critical effect in terms of what happens when the light is radiated down upon them. So in an ink droplet, you've got your pigments, you've got your photoinitiators, and when the light shines down upon that dot there, it depends whether you've got shortwave, which is depositing its energy towards the surface, or whether you've got long wave, which is therefore penetrating down a bit deeper through the ink. If you've got heavily pigmented inks, then you want long wave, which penetrates better. On a fairly thin ink, then generally the surface cure is more important. Looking inside the ink, what actually happens there, you've got a mixture of photoinitiators, and these actually have to be tuned to suit the output of the UV lamp. So if you look here at the output of an arc lamp, and that's those turquoisey blue peaks on the graph, You've also got this large purple spike here, which represents the output of a UV LED. With your Mercury arc lamp, photoinitiator 1, that's the blue curve, is going to give you quite a good curing result in that component. But when you get towards the longer wave output of the spectrum here, where the LED is, it's not going to work so well. So you need to choose a different photoinitiator, such as this red curve here, photoinitiator number 2. So the photoinitiators have to match the wavelength of your UV light source, otherwise the curing is going to be way off the mark. Let's take a look at how the two technologies actually perform, what their functional differences are, and how they generate the UV light. So with a Mercury arc lamp, this consists of a sealed quartz tube with an electrode at each end. Inside the tube, you've got a mixture of argon gas and a small quantity of mercury. When you apply a high voltage electric current to those electrodes, the argon inside the lamp ionizes. This causes the mercury to heat up, it vaporizes, and then inside this electric arc with the vaporized mercury, you get an output of UV light and visible light. Comparing that with an LED, this works very differently. This is a light emitting diode, and this consists of a sandwich of two semiconductor materials with a very small gap in between them. That's known as the band gap. And when you apply an electric current to this semiconductor sandwich, you get electrons which jump from a high energy potential down to a lower energy potential. And in that change in state, they emit a UV wavelength. And the exact UV wavelength that comes out across there depends on the gap between the two semiconductors. Now, obviously, this takes place on a very small scale, so if you've got a wide area that needs to be covered, you therefore need an array of many, many individual diodes. Let's compare the output of the two systems in a little bit more detail. So with a Mercury arc lamp, you've got again your turquoise blue coloured output chart here. You're getting shortwave and longwave UV radiation. Now for an ink manufacturer, this is quite good news because it means there's an abundance of photoinitiators you can choose from. You've got a lot of choice and potentially you can make the ink formulation relatively inexpensive. You also get a significant amount of infrared output. That's the heat that comes from the process involved in generating UV light. So again, where heat is required, you get a curing benefit there. With LEDs, you get just a single, well, it's actually not a single output, it's a distribution of outputs which are very narrow in their bandwidth, and they're clustered around a single wavelength towards the visible light end of the UV spectrum. So it's long wave output only. It's very high intensity. You'll notice there on the graph that you get a very high peak of this UV LED output. Now what this means for an ink manufacturer is there are potentially some challenges because your range in photoinitiators is a lot reduced, and there are obviously light stability issues there. If your photoinitiators respond so close to light that it's almost on the visible light spectrum, there can be challenges there. However, the benefit is that the through curing, the deep curing of this LED curable ink is a lot more effective. You also get very little output of heat, so on some substrates this gives you potentially a big advantage there. In the past, it wasn't really so practical to cure on these sensitive materials. With a single pass printer, the only way you could actually cure at all on a very sensitive substrate was to wrap it around a chill roller as it passes underneath the lamp and have the lamp that's mounted straight on top of that chill roller, which is fine if you're printing on a web and it's a continuous web, but if you're doing any kind of semi-rotary processes, or indeed if you have a wide format printer, then that's really not an option. So the only solution there is today to use a UV LED system. Now the advantage of that is, unlike with a mercury lamp where it's radiating infrared and ultraviolet energy in 360 degrees, quite neatly with your LED, the heat is all going in one direction, that's absorbed by the heatsink behind the light source, and all of the UV conveniently goes down towards the substrate. So with very little heat, that means that there's no stretching of the material. The print job itself is much more easy to keep in register, and without having chill rollers on the press, that reduces the part count of the machine. Let's take a look now at the difference in efficiency between a mercury arc lamp and a UV LED. So if you've got your turquoise here, which represents arc, you've got the purple, which represents LED, it might actually come as a surprise to some that for your energy input, the effective UV output that you get from the two technologies is actually broadly similar. So with a mercury lamp, you're at about 28% efficiency, and with an LED, you're somewhere around 35% efficiency. The difference is that the LED is a lot more effective than the mercury arc. So whereas with a mercury arc, you'd be running at about somewhere between 140 and 180 watts per centimetre input to the lamp, with an LED, you're going to be around about half that, with 75 watts per centimetre input. And the reason for that is because of the higher intensity of the UV LED. One of the big opportunities there is also with LEDs is to save energy when the machine is stopped, so that's on standby power. With a mercury lamp, you can't simply just switch it off. When the machine stops, the lamp drops down onto a standby power, which is typically these days in the region of 25 watts per centimetre. In the past, it could have easily been double that. And then you have a mechanical shutter which will close underneath the lamp. Now, with an LED, that's just simply not necessary. It switches off and you consume no power whatsoever. How do we see this developing? Now, obviously there is a scope to improve this 35% efficiency there. In the lighting sector, efficiency is much higher than that, and as the volume of LEDs increases, we foresee this going up. With the mercury lamps, I don't think there's as much scope to actually increase the efficiency as you do with LEDs. It's quite a mature technology. Yes, there is still ongoing development to increase the efficiency of power supplies, to increase the efficiency of reflector technology, but the actual physical properties of the UV lamp itself, there's fairly limited scope for actually increasing that by a significant amount. Whereas with LEDs, there is a bigger opportunity because the technology, relatively speaking, is still in its infancy. There are also quite significant benefits with LEDs in terms of increasing productivity. So with instant on-off switching, no time is wasted waiting for lamps to either warm up or cool down. And the lamp life, the service life of an LED is also greatly extended compared to a mercury lamp. So if we compare now the difference here, with an LED, it's quite possible to get in excess of 20,000 hours operating time. And with a mercury lamp, a typical lifetime would be around 3,000 hours. But that includes not only the operating time, but also the standby time. So on machines with a relatively low duty cycle, where the lamp spends a lot of time on standby, you're still using your lamps, whereas with an LED, that's off. So potentially the LED would actually outlast the lifetime of the machine which it's fitted to. Let's take a look at how many times you'd have to change your mercury lamp over the lifetime of the LED. So the blue curve here represents the lifetime of one LED lamp, and the red curve, each red line here represents the lifetime of a mercury lamp, and then it has to be changed. So over the lifetime of the LED, you'd probably have to change your UV lamps at least 10 times, depending on the duty cycle of what your press is. Other productivity benefits include the fact that with a lamp you've got far more serviceable parts than you would do on an LED. There are reflectors, so you don't have to change reflectors or change any lamps out. Sorry, you don't have to clean reflectors or change lamps with an LED. And there's no shutter mechanism either to maintain. So all of these factors contribute towards increasing the productivity of the machine. So what about the capital costs? So LEDs potentially can be quite cost effective at a narrow width. And one thing you do have to consider though is as you go wider, if you double the width, proportionately, you approximately double the cost. Whereas with a mercury lamp system, that increase in cost is a lot more gradual and quite a lot more forgiving. So for very wide systems, it's still the technology of choice today to use a mercury lamp system. Let's just summarize some of the strengths and challenges of the two technologies. So with an arc lamp, they tend to be the preferred technology for single pass printing. They have a lower investment cost. The ink sets that you have are widely available and well proven, and the cost of those inks is still in many cases a little bit lower than what you might have to pay for an LED equivalent. The downside is that the lamps are less controllable, the substrate temperatures are invariably going to be higher, as is the energy consumption, and from an integration point of view, lamps are bigger, so to fit them into the confined spaces that many machines only have available is quite a challenge. Now, as far as LEDs are concerned, for the end user, they offer the benefit of energy savings and a reduction in heat, so the range of materials that can be successfully processed on a machine is going to be a lot higher. The lamps also don't need to be changed very often either. Now, for the integrator, they offer the obvious benefit of being easier to integrate, and also they give a very precise output on demand. The downside is that as you get long, the investment cost is rather high, the spares are expensive if you have to have any, and potentially the ink costs are still, at the moment, a little bit higher, although in the future we do foresee that coming down. As will the availability of the inks, that's also going to increase. So what does that mean for the future? The way we see the future developing is that UV systems will be hybrid, and what that means is you'll be able to have two interchangeable UV technologies, that's mercury arc and UV LED, working from one common interface and common power supply. So that means from an integrator's point of view, there's only one electrical integration that needs to take place, and whether you're offering to your customers a mercury machine or a machine fitted with UV LEDs, all of the control and integration is identical. Here's a demonstration of how a UV system of the future would operate. So in the way that everyone's familiar, you've got your mercury arc lamp with its mechanical shutters. These open, the lamp starts to increase as the machine speed increases, then it will ramp down again as the machine slows down, comes to a stop, and the mechanical shutter closes. Now where the different point comes in, that can simply be switched off, and you have a cassette, and that cassette can be withdrawn from the housing after the lamp has cooled down. And once that's taken place, the LED cassette can be inserted. Now with LEDs, there is no warm-up time. The lamp's ready to start immediately, and as soon as the press starts, that power increases up from 0. There's no standby power. There's no mechanical shutter. The LED cassette's detected by the same power supply that was running the mercury lamp just moments ago, and it delivers the correct low voltage direct current and runs that lamp automatically. So here, as we see, the press increases, the power just comes up from a very low, from a 0 level up to full power, and it can go back down again. Now, what you also get that's different from a lamp is the power is very controllable, so you can have exactly what level of power you need as soon as you want it, without any ramp up. So if you're running on, perhaps on the industrial side, you're not running on a continuous like web or sheet. You've actually got individual industrial products that are coming through. So if you're printing on bottles or tubes, the lamp can be off, and you might say you actually need 100% power to cure each bottle as it comes through. Then you have 0 power, and then when your bottle comes through, you just flash on at 100% and flash off again. So it's a lot more versatile and controllable. So why, apart from that, would you wish to use a hybrid UV system? It gives the end user the option to optimize on every single process. So on some machines, and if anyone was at Label Expo, they'd have seen that there's a lot of digital units being integrated with conventional flexo presses. So you've got digital, potentially you've got flexo, which is running a base white at the beginning of the machine, an opaque white, and then right at the end you'll have a UV varnish. So with your other process colors as well, you might have some low migration inks in there, for instance. Arc lamps will offer you always the lowest investment cost, and LEDs will offer you the lowest energy cost. For your base white process, you can optimize on performance, because LEDs will give you by far better performance with a base white than ever you'd hope to achieve with a mercury lamp. On the other hand, with a varnish, you really get a better result using mercury lamps. And as far as pinning is concerned for the digital units, that's really only an option by using LEDs. So I'll say a few words about that. The purpose of pinning is to actually freeze that ink dot on the material without fully curing it. So when you print the other colours next to it, they don't bleed to each other, and then you can fully cure those at the end of the machine. So what happens if you try and use that process with a mercury lamp? The shortwave radiation, which is deposited near the surface of the ink dot, causes it to skin over. You get a very quite impenetrable, fully cured layer there, which goes over the surface. Now, when you get to the end of the machine and fully cure, or attempt to fully cure with your mercury lamp, you can't, because the final radiation can't actually penetrate through there. The other issue is that mercury lamps, they're not as controllable, so they do have a minimum power which is sustainable to run them at. And when you run them at that very low power, still you get quite a lot of high intensity shortwave radiation. That reflects up off the substrate, and surely it's going to end up straight into the print head. There's no easy way of constraining that light and focusing it right down where you want it to be. Now, with an LED, you get this very controllable, easily focused, low intensity, low power, should I say, long wave radiation. So that'll penetrate the ink, and it won't cure over the surface. It will just lightly gel it so the dot doesn't move. And then it avoids also this issue of the shortwave light being reflected up into the inkhead and curing up in your inkjet nozzles. So, why hybrid? That's to fully optimise the product range of either the end user in terms of what jobs they can run, or indeed for an integrator to optimise the range of machines which they can offer and the value that adds for the customer. ARC and LED are both going to be required in future. So you get the benefits of having two technologies integrated on one common platform, and what that means is that the complexity of the integrator's range of machines is greatly reduced, as is the engineering cost, and the flexibility of the whole product range is increased, and so too is the speed to market, which is also very important. So the way we see it is that the printing machines of the future, the most flexible, the most productive printing machines, will all run hybrid UV curing systems. So I'd like to thank you for staying to the end to listen to my talk and invite any questions.